Lesson 7H, Linear Two-Body Systems. This will be frictionless examples. Here's an example of a linear two-body system on a frictionless surface. Let's assume the wire is ideal, meaning it's weightless, static, and unbreakable. In certain situations, we can group the two masses into a single mass for our calculations. All parts are accelerating at the same rate. Recall, tension at both ends of the wire will have the same magnitude, but in opposite directions. They are equal but opposite. Example number 1 has a 2 and 3 kilogram box joined by a string on a frictionless surface. They are being pulled along with the force of 20 newtons to the right. Here is a diagram of the boxes. We will calculate acceleration and string tension. Let's finish labeling our free body diagram, where the coefficient of friction is 0. The force applied is 20 newtons to the right. On the first mass, force gravity and force normal are equal, since the object does not fall or rise along the table. This is also true for our second mass. Force gravity and normal force are equal too. Force friction will be 0 since the objects are on a surface with a coefficient of friction of 0. Now force tension in the wire will be along the entire length of the wire. The tension will be equal but opposite at the ends of the string. Let's calculate acceleration. For this problem, we can ignore force gravity and force normal, so our free body diagram can look like this. Who wins the tug-of-war? Applied force or friction force? Well, applied force wins as friction is 0 and the objects move to the right. F net is the sum of all forces. Remember, forces are vectors, so they include direction. Net force equals force applied minus force tension from mass 2 plus force tension from mass 1 minus force friction. Since the two force tensions cancel each other out and force friction is 0, our equation is simply force net equals force applied. Remember, the formula for F net, or net force, is mass times acceleration, which makes the equation force applied equals mass times acceleration. Force applied equals mass 1 plus mass 2 times A. 20 newtons equals 2 plus 3 times A. 20 newtons equals 5 times A. Our acceleration is 20 divided by 5, which makes it 4 newtons per kilogram, or equivalently 4 meters per second squared. To calculate tension, we look at each mass individually. Let's start with mass 1. Now who wins the tug-of-war? Tension or force friction? Well, since force friction is 0 and the object moves to the right, force tension wins. Net force on mass 1 is therefore force tension plus force friction. Since force friction is 0, F net is simply force tension. Force tension equals net force. Remember, the formula for net force is mass times acceleration, which makes it force tension equals mass 1 times acceleration. Force tension equals 2 times 4 newtons per kilogram, which we had just calculated earlier. Force tension is 8 newtons. Force tension on the wire at mass 1 is 8 newtons to the right. We can also calculate tension using the second mass. We have explained that tension along the wire will have the same magnitude at each end but in opposite directions. We know that the tension should be 8 newtons. Let's try mass 2 and confirm this. Who wins the tug-of-war at mass 2? Is it force applied or is it force tension and force friction? Force applied wins over force tension and force friction as the object moves to the right. Force friction is 0, so that makes F net equal force applied minus force tension. Isolating force tension, we have force applied minus force net. Isolating force tension, we have force tension equals force applied minus net force. Remember, the formula for net force is mass times acceleration. Force tension equals force applied minus mass times acceleration. Force tension equals 20 newtons minus 3 times 4 newtons per kilogram, which we had calculated 2 steps earlier. Force tension equals 20 newtons minus 12 newtons. Force tension is 8 newtons to the left. Force tension along the wire has the same magnitude of 8 newtons.